Welcome back to MetaVerse Update. First up, Fumiya Hanamura and colleagues are unlocking universal computation with non-Gaussian states of light, drastically improving success probabilities and slashing photon requirements. Next, we're diving into quantum computing efficiency. Toshiaki Kaji and his team at the University of Tokyo have developed the Aqcel Optimiser, slashing circuit costs and boosting fidelity by cleverly reducing two-qubit gates. Then, get ready for a mind-bending look at energy flow. Vansh Kaushik, Sayan Choudhury, and Tanay Nag are creating synthetic lattices that enable quantized energy exchange between drives, with huge implications for quantum materials. And finally, Lorenzis and his team are pushing the boundaries of quantum machine learning with quantum extreme learning machines, achieving incredible accuracy through evolution and dimensionality reduction. Don't miss out on these game-changing updates. Make sure to like, subscribe, and hit that notification bell so you never miss a beat. Quantum computation is getting a massive upgrade thanks to non-Gaussian states of light. This breakthrough is about to make universal computation more accessible and reliable than ever before. Scientists, including Fumiya Hanamura, Kan Takase, and Hironari Nagyoshi, have introduced non-Gaussian control parameters, a game-changing method that optimizes the generation of these crucial quantum states. This new approach dramatically cuts down the photon requirements by a factor of 3 for certain states like GKP states, and significantly boosts the probability of successful state creation. Imagine preparing complex quantum states with far fewer resources and much higher success rates. This is exactly what their research achieves. They've demonstrated these gains across various states, including CAT states and GKP states, paving the way for more practical and scalable quantum technologies, and ultimately, fault-tolerant quantum computation. This isn't just an incremental improvement. It's a foundational shift in how we can harness non-Gaussian states of light for powerful quantum applications. This development is already creating a buzz, with the quantum community excited about the increased feasibility of advanced quantum experiments. The potential for more efficient quantum computing and sensing is immense, promising to accelerate discovery and innovation across the field. This quantum leap in state generation is just the beginning. Next, we'll explore how a new optimizer is making quantum circuits dramatically more efficient and accurate. Quantum computers are powerful, but their efficiency hinges on how well we can run algorithms on them. Researchers are constantly seeking ways to minimize computational cost and maximize fidelity, especially for near-term devices. Now, Toshiaki Kaji, Koji Terashi, and Ryu Sawada from the University of Tokyo have refined their state-dependent circuit optimizer, Aqcel, making it even more potent. This improved Aqcel intelligently reduces unnecessary calculations by focusing on the specific states of control qubits, meaning it only performs operations that are truly needed. By incorporating a state label manager and a pair removal process, Aqcel aggressively shrinks the number of two-qubit gates, the most error-prone operations required to execute a quantum circuit. When applied to circuits for complex tasks like simulating Parton showers, a crucial process in high-energy physics, Aqcel demonstrates a significant reduction in gate counts and a marked improvement in overall fidelity compared to existing methods. This optimization is critical for making quantum computations more reliable and accessible on current hardware. The ability to reduce gate counts directly translates to lower error rates and faster computation, bringing us closer to practical quantum advantage. From optimizing circuits to controlling energy, the next frontier is truly mind-bending. Get ready for a deep dive into how scientists are creating synthetic lattices for quantized energy exchange. Controlling energy flow in quantum systems is key to unlocking new technologies. This research delves into creating artificial structures that mimic complex material properties, allowing us to manipulate energy in unprecedented ways. Investigators Vansh Kaushik, Sayan Choudhury, and Tanay Nag have developed a novel approach using a quasi-periodic drive on a 4-level quantum system. This creates a synthetic Floquet lattice, essentially a temporal landscape where energy can be actively pumped and exchanged. They've demonstrated that this system can behave like quantum spin Hall insulators and higher-order topological insulators, exhibiting quantized energy exchange directly linked to topological properties like propagating edge modes, characterized by a spin-churn number. In a fascinating twist, for a higher-order insulator, this energy exchange ceases, indicating the presence of localized corner modes. The fidelity of the system's time evolution acts as a clear indicator of its topological phase, showing how stable and controlled the energy flow is. This ability to precisely control and characterize energy movement opens doors for novel quantum technologies and a deeper understanding of exotic quantum materials. This breakthrough is generating excitement for its potential applications in areas like quantum sensing and novel electronic devices. The ability to engineer energy flow at a quantum level could revolutionize material science and quantum information processing. But the innovations don't stop there. We're heading into the realm of quantum machine learning, where new machines are achieving astonishing accuracy. Quantum machine learning is rapidly evolving, promising to unlock new computational power. Researchers are exploring novel architectures that simplify training while maximizing performance, even on current hardware. A team led by A. de Lorenzis, M.P. Casado, and Enlo Gullo is making waves with their Quantum Extreme Learning Machines, or QELMs. These machines simplify the learning process by focusing on the final layer and ingeniously combine dimensionality reduction techniques with quantum dynamics. What's remarkable is that they've identified a critical transition point where the machine's accuracy sharply jumps and then plateaus at a level competitive with highly complex quantum systems. Crucially, this learning process is fast and doesn't seem to depend on the size of the quantum system, suggesting these QELMs might be more easily simulated on classical computers than initially thought, despite their quantum nature. The research shows that even with a specific Hamiltonian like the XX model, these machines can achieve performance comparable to systems driven by random unitary transformations, highlighting the importance of information spreading in their effectiveness. This discovery has significant implications for developing scalable and efficient quantum machine learning algorithms. The potential for applications in areas like image recognition and complex data analysis is immense, making quantum learning more accessible than ever. And that wraps up our incredible quantum updates for today. Stay tuned for a lightning round recap and your chance to win. And that's a wrap on this episode of MetaVerse Update. We saw Fumiya Hanamura's team unlock universal computation with better light states, Toshiaki Kaji's group optimize quantum circuits for peak performance, Vansh Kaushik's team master quantized energy exchange, and A. de Lorenzis' researchers achieve high accuracy with quantum extreme learning machines. If you found this update mind-blowing, smash that like button, subscribe to MetaVerse Update for all your quantum news needs, ring that notification bell so you don't miss a single upload, and drop a comment below telling us which breakthrough excited you the most. Don't forget to follow us on all our social channels for more exclusive content. See you next time.